So, hello everyone. Today I would like to present the paper that is utilizing skip frames in action repeats by pseudo actions. So this paper is presented in UNIP 2020. This is an IL paper. So let I recall about what's the reinforcement learning. Reinforcement learning is an area of machine learning concerned with how software agents ought to take actions in an environment so as to maximize some function of cumulative reward. So in the reinforcement learning, we have agent and environment. At each time step, the agency observation of state of the world and then made an action to the environment. The environment return the next state and also a reward signal. And the goal of the agent is to maximize its cumulative reward, also called return. Reinforcement learning methods are ways that the agent can learn behaviors to achieve its goals. So usually the problem of reinforcement learning is modeled with a Markov decision process, MDB. The Markov decision process is defined by a tuple S, A, P, R, rho, gamma, and H. Here S is the state space, A action space, B here is the transition probability, and R reward function. So we also have the distribution of initial state, rho, rho 0, and we also have discounted factor gamma. Horizon here is the how long of one episode is. So model the reinforcement learning problem as an MDB, and we will try to find a policy bias so that it maximize the return when it acting on the environment. So this paper concerned the problem that when we roll out on the environment, we take an action A from the agent state, and then we will do some action repeat here. Is the okay? We will do the same action for a number of action repeat. This is the common practice in any reinforcement learning algorithm. And usually the number of action repeat here is 2, 4, and 8, depend on the environment that you work on. So the total sample when you roll out on the environment will be equal to number of environment states, and it will be equal to the number of roll out multiplied with the number of action repeat. So if the number of action repeat here is high, then the total sample will be high. It will be concerned as sample inefficiency if we cannot utilize on the observation that we get when roll out. So as a common practice, intermediate observations are discarded during roll out. So it is weighted. So this is the problem of this paper, and the question is that how we can utilize the information of the intermediate observations efficiently. That's the problem this paper want to solve. So let's explain more about how they discuss the observation during rollout. So as time t, we get the observation s0. So we test the agent step with observation s0, and we get action a0, and we will repeat this action a0 for a number of action repeat. Here in this case, we repeat the action 4 times. We take the action 0 and we get to s1, and we take action 0 here again, because we repeat the action a0 here, and we take s2 and then s3, and then we jump to the time step t plus 1. All the observation s1, s2, and s3 are discard. The observations are discard, so it's weighted. So let's mathematically formulate for this problem. So let's call environment step the environment step, agent step the agent steps. Here is the number of action repeat. So the agent will select action S time A0, and then AT, and then AT. In conventional reinforcement learning, action repeat mean that A0 will be equal to A1 to AT minus 1, and AT will be equal to AT plus 1 to A2T minus 1, and etc. So observation used for training are just S0, ST, and S2T. So in conventional reinforcement learning, the benefits of action repeats is that if we use action repeat, we will make clear the difference between actions, and then it will be more stable training. Using action repeat will be also facilitate the exploration and reduce the computational cost, because we don't we just repeat the action, we don't compute the action through agent dot step, so that we can ensure that real-time operation when performing inference. So come back to the problem, that how can we utilize the intermediate observation to increase or improve the sample efficiencies. This paper proposed two approaches. The first is a nice approach, mean that we can just use, for example, here is the intermediate observation, and we can create the transition from the intermediate observation by create a tuple of SKT plus L, AKT plus L, and SKT plus L plus T. Mean that this observation, and we test this action, and we jump to the next observation here. So SKT plus L equal to SKT, as we explained before, using action repeat. So using this nice approach, it is not very good, because the action AKT plus L is not repeated time as original AKT, because here it is not AKT, it's different with AKT. So the better approach is that we somehow calculate again the action AKT plus L. So they call that the pseudo-action. The problem right now is the way how to calculate the action A hat KT plus L to create the transition here. So they propose two ways of calculation the pseudo action. The first way is that for continuous action space, we just average out all the action that we test in the intermediate observation to create the pseudo action. So this is the formulation for average out the action of intermediate observations. For discrete action, we cannot test the average out directly because it's just a number. So they propose to embed it into the latent space, embed the action, discrete action into the latent space better. And then using the embedding feature, we can average out all the embedding feature of action to create the embedding of the pseudo action. They propose also a new architecture for embedding the action in the discrete action space control. This is a new architecture. So this is the pseudo algorithm. When we create a minibus of the training for Q network, we input replace buffer minibus size and action with parameter t, and we from k to n, any the number of minibus size, we sample a sequence of transitions, also contain intermediate observations, and we calculate the state, next state, reward for each transition, and also we calculate the action by pseudo action as I described before, and we add the transition into the buffer, into the bus side, the bus. And this part will be used for training any algorithm that we concern. So the results of this paper, they show that on continuous control tasks, which the skip frame of 4, the improvement using pseudo action is just a little bit, but if you use skip frame like 8, the improvement is very big, like this one. Also, the same result is reported using discrete control tasks, and with small skip frame, the improvement is a little bit, but with the last skip frames, the improvement is very large, and also the variance is reduced at in the figure. So that is all about this paper. So any question about that?